So we're live now, and everybody wants to say hi to the band kids.
Arnie!
Okay, all right. So, anywho,
Wait, is it filming your face?
it will be filming part of my face in the upper right-hand corner. All right. So, yesterday we talked about metallic bonding, and prior to that we talked about ionic bonding, and then we had an entire unit on covalent bonding. And so here is a side-by-side comparison of the three types of bonding that you guys are going to be responsible for being able to explain on the AP exam in May. In ionic bonding, the major thing, well, I guess the thing that's the same about all of them is they all start with many atoms, but the major difference is that ionic bonding creates that crystal lattice structure over here. And as a result of it creating that crystal lattice structure over here, what we end up with is the alternating positive and negative charged atoms next to each other, and they create the ions. With covalent bonding, we take atoms, and then as a result of taking atoms, they form compounds, but they stay neutral, so they're sharing electrons. And then lastly, with metallic bonding, the major difference here is the electrons are delocalized, so they are being used by many atoms at the same time. So we have delocalized for metallic, they're sharing electrons for ionic, and they're for covalent, and they're transferring electrons for ionic. Okay, so super fast. Well, we're not going to go that far today. I just put them all on here. All right, so anyway, we have intermolecular forces versus intramolecular forces. We learned about that stuff last year. Intramolecular forces are the bonding forces that hold individual molecules together. So your nonpolar covalent bond, your polar covalent bond, your ionic bond, metallic bonds, those are intramolecular. Whereas intermolecular forces are the intermolecular forces, the things that hold molecules together. So we're going to go back to covalent compounds a little bit. Intermolecular forces tend to draw the molecules together, while the kinetic energy of the system tends to cause molecules to move apart. So intermolecular forces is essentially this giant dance between how strong the molecules are held together by their attraction versus how much kinetic energy the system has. One thing that was made very, very clear to me a couple of years ago is that please, on the AP exam, if it asks you to identify what force is present, don't write IMF, don't write intermolecular forces or IM forces. Actually write out the word or the phrase intermolecular forces. They want to see the word for some reason. I'm not 100% sure why. It's just that's what I was told. So make sure that that's something that you get used to saying or doing or writing or cycling. Okay, so we're going to go through the different types of intermolecular forces. So this is kind of a review for us, hopefully. The first one we need to talk about is the ion dipole forces. The ion dipole forces are what contribute to the fact that a lot of ionic compounds will dissolve in water or other substances for that matter. The interactions between the oppositely charged ions are stronger than the ion dipole interactions, and the ionic compound will not dissolve in water at that point. So in the case of sodium chloride, which is what this particular compound is, we take table salt, we throw it into water. Well, the issue is that the attraction coming from the positive end of the water molecule is stronger than the intermolecular or intramolecular force between the sodium and the chlorine. And as a result of that, we can separate the ions themselves, and they become completely surrounded by water molecules. So the big thing with the ion dipole forces is that the water molecules have a stronger attraction to the ions than the ions together do. As a result of that, they're able to separate and dissolve in water. And when they do that, when they're dissolved in water, they end up completely becoming encircled by the water. As a result of that, we now have individual ions that are floating around, and they're completely engulfed by water in 360-degree fashion. So there is a limit to the amount of salt or things that we can dissolve in water. And what does that look like, I guess, when we dissolve too much? What do we call that? That'd be, well, not supersaturated, but it's saturated. It's like oversaturated. Supersaturated is when something is dissolved in water, but it's more than there should be. Does that make sense? Saturate. Right. So if the temperature is raised, we can dissolve more. We lower the temperature, it falls out of solution again. So there's that. Another type of intermolecular force that we are going to talk about would be the dipole-dipole forces. Dipole-dipole forces occur in polar compounds when the positive pole from one molecule attracts the negative pole of another molecule. Larger the dipole equals stronger attractions, equals higher melting points and boiling points. So in the instance where we have solid CH3CN versus liquid CH3CN, note that the dipole-dipole force is a lot shorter in between these molecules here in the solid than it is in the liquid. And one of the things that we need to keep track of here is that the attractive forces are still present in the liquid. That's what's kind of holding them together and allowing them to slide by one another. But the repulsive forces are also what's allowing them, are the major part that allows them to slide by one another. So there's this sort of balance of attractive versus repulsive forces in liquids. And if we increase the kinetic energy by, I don't know, adding heat, okay, as a result of adding heat, we can increase the kinetic energy, and then the kinetic energy of the system increases, and the dipole-dipole forces are weaker than the kinetic energy, and then we start to do, then the solution starts to do what? If I add heat to a solution and my kinetic energy is greater than the attractive forces, what's going to happen? They'll break apart, which would start forming what state of matter? Gases. So then another intermolecular force that we need to talk about is hydrogen bonding. And hydrogen bonding is a special type of dipole-dipole force. We have to be aware or cognizant of the fact that hydrogen bonding tends to occur when nitrogen or oxygen or fluorine are present with hydrogen bonds only. So when oxygen is bonded to hydrogen, or nitrogen is bonded to hydrogen, or fluorine is bonded to hydrogen, that's when a hydrogen bonding can occur. We want to make sure that we remember that by calling it FON, fluorine, oxygen, nitrogen. So if you can identify that a dipole-dipole intermolecular force is occurring and a hydrogen is bonded to an oxygen, then that becomes a special type of intermolecular force that we call hydrogen bonding. So in this case, the slightly positive side of oxygen is attracted to the slightly negative side of, the slightly positive side of hydrogen is attracted to the slightly negative side of oxygen, and we create this sort of lattice structure that makes water kind of do whatever it wants compared to other liquids. Any questions about intermolecular forces? All right, then. Another intermolecular force that we are going to be, well, we should probably answer some questions first. So which of the following substances is hydrogen bonding likely to play an important role in determining physical properties? Methane, hydrazine, or hydrazine rather, methyl fluoride, and hydrogen sulfide. So if we remember that methane is CH4, when we draw that structure, it looks something like this. And hydrazine would look something like this. Let's see. And then methyl fluoride would look something like this. And then hydrogen sulfide would look something like this. Okay, so the question is, which of the following substances would we imagine that, or would be able to identify that hydrogen bonding would be present? And one of the things that we can immediately get rid of is we can immediately get rid of the methane and the hydrogen sulfide, because even though hydrogen is bonded to something, it is not bonded to a fluorine, an oxygen, or a nitrogen. So those are automatically not participating in methane or in hydrogen bonding, which then leaves the hydrazine or the methyl fluoride. And we can get rid of this one because even though fluorine is present, it's bonded to a carbon, not to a hydrogen, which means that this is the particular molecule that will allow hydrogen bonding to occur, because there is a slight dipole that goes here. And as a result of that, we have a slightly positive side, a slightly negative side, a slightly negative side, a slightly positive side. So this is the chance, or the opportunity rather, where we would have something like some hydrogen bonding might occur here. So the nitrogen and the hydrogen would be attracted to one another because here's the slightly positive, slightly negative, slightly negative, slightly positive. Does that make sense? Sir?
Hydrogen is H2 and then H2. Is there like a reason like there's only two H's?
That I forgot to draw a couple of H's. Sorry.
So the hydrogen has to be connected in the molecule to a fluorine, oxygen, or nitrogen?
Yes.
Okay.
Okay. So the question was, does the hydrogen have to be connected to a fluorine, oxygen, or nitrogen in order for hydrogen bonding to be present? And the answer to that question is yes. It has to be connected to a fluorine, hydrogen, or nitrogen in order for hydrogen bonding to occur. We go to that. Yes. In order for, so dipole intermolecular forces are when there's a dipole present, which means that one of the atoms in a bond is a little bit more, has a stronger electronegative attraction to the electron in the bond. Okay. The special type of that is hydrogen bonding. And hydrogen bonding is still dipole, but it is very, very specific when the nitrogen is bonded to the hydrogen in some way, shape, or form. And so the attraction occurs between the nitrogen and the or hydrogen of something else. If that makes sense?
Mm-hmm.
Oxygen or fluorine. Okay. Another type of intermolecular force would be the London dispersion forces. Every single covalent compound exhibits some London dispersion force. Also, don't write LDF. Write London dispersion forces on the AP exam. They will mark it wrong. I'm not sure why, but that's what I've been told. So what ends up happening is that these moving electrons bunch up onto one end of a molecule, creating what we call an instantaneous dipole, which induces a momentary dipole in adjacent molecules. So like chlorine bonded to chlorine, on paper, the electronegativity difference would be 0. And so as a result of that, the implication would be these two electrons right here are being shared equally. The issue is that that's not true. These electrons here and here, they need to both be on one chlorine at a time for that chlorine to feel as though it is satisfied or have 8 valence electrons. So this this electron might spend a couple of seconds over here. And when it spends a couple of seconds on that chlorine, that means that this side of the molecule becomes slightly negative and this side of the molecule becomes slightly positive. Well, if that's the case, when the electron goes back, it goes back to being neutral. But if I happen to have a second chlorine atom over here, or a chlorine molecule over here, where the electrons happen to be shared equally at that particular point in time, when this molecule becomes slightly negative right here on this side, it automatically forces this side of this chlorine to become slightly positive. And as a result of that, this side becomes slightly negative. So it's almost like a domino effect. If I were to have a bunch of chlorine atoms that were just happening to be hanging out in a jar, and I took one of them and the electrons shifted and made the bond slightly polar, then what would end up happening is all of the atoms, all of the chlorine molecules would start to create this instantaneous dipole, and as a result of them creating this instantaneous dipole, they would start to stick together. So that's what London dispersion forces are. Does that make sense? It's an entire molecule that becomes polar that shouldn't be. We good so far? Okay. And then, so here's an example, again, of what that would look like. Here's separated chlorine molecules. And one of those chlorine molecules creates an instantaneous dipole, creating an instantaneous dipole on another chlorine molecule, and the whole mess of them end up being attracted through that single instantaneous dipole. So these are, one would consider them originally neutral, but that electron, or one of the electrons, or both of the electrons shift to one side of the bond, and when they shift to one side of the bond, what ends up happening is the electrons create a positive side and a negative side, and then that positive side, negative side allow for attraction with other nonpolar molecules, like another chlorine molecule there. Does that make sense? So far, so good? Getting closer to the end here. So this is a flow chart that might help you when it comes time to identify what type of intermolecular forces are present. So we would start with, are ions present? And if you can answer yourself that ions are present, then you would be asking yourself, is it a polar molecule? If it's a polar molecule and ions are present, we would call it ion dipole intermolecular force. If there are no polar molecules present, we would just call it ionic bonding, and that's that. But if there are no ions present, we would ask ourselves if there are polar molecules present. If there are no polar molecules present, we would call that London dispersion forces. If there are polar molecules present, then the question is, are hydrogen atoms bonded to oxygen, nitrogen, or fluorine? If there are, then hydrogen bonding is present. If there are not, then it's just dipole-dipole. This whole business about van der Waals forces down here is something that used to be really important in chemistry, and it's not quite as important anymore. We're just pretty much okay with this scale of going from left to right gives us the weaker of the intermolecular forces all the way out to the stronger of the intermolecular forces. So LDF is the weakest force. Ionic bonding is the strongest because the electrons are actually transferred. Does that make sense? Okay, cool. So in the next problem here, it asks us to identify what type of forces would exist between the following pairs of molecules, and then draw a model to show how two substances form attractions. So in the case of H2S and HBr, I've identified those to be dipole-dipole. So when I draw H2S, it looks something like this. And HBr would look something like this. And I know that bromine is more electronegative than hydrogen, so it's going to have a dipole moment like that, okay? And I know that sulfur is more electronegative than hydrogen, so it's going to have dipoles that look something like this. And as a result of that, we would have some attraction between the slightly positive hydrogen and the slightly negative bromine, so that's why it's dipole-dipole. So far, so good to that? Yes, no?
Yeah.
Okay. The next one is Cl2 and CBr4. So chlorine, Cl2. On paper, this is a nonpolar molecule, so there should be no reason for it to bond to anything else. And then we have CBr4. And also, this is going to be a nonpolar molecule because each of the 4 bromines are being pulled in opposite directions with an equal amount of force. So there's no reason for that to have any attraction to it whatsoever. So if there is no reason for these 2 things to have an attraction, we do know that there is a slight amount of attraction, and we call that London dispersion forces. Does that make sense? And then lastly, KNO3 and H2O. So KNO3, this is an ionic compound because it's a metal and a nonmetal. So I have potassium ion floating around, and I have nitrate ion, NO3 minus 1 floating around, and we're going to dump it in water. So I'm going to have oxygen here, or water here, and water here. And because of the polarity of the water molecule going in this direction and going in this direction, there is a force of attraction here, and there is a force of attraction here. And ideally speaking, because this is dissolved, this guy would be completely surrounded by water, and this guy would be completely surrounded by water. Does that make sense? Okay, now, this is the homework assignment for the evening, but there's one more slide that I want to do, which comes next. And it talks about Coulomb's law. So Coulomb's law, as we've talked about multiple times, and this is not the same slide this time, basically says the stronger the attraction between 2 charged particles, the more difficult they are to pull apart. Does that make sense? So the question says, consider the ions copper plus 1 and copper plus 2. Which ion would form a stronger Coulombic attraction to water? Draw a model that indicates how water is attracted to each ion, and be sure to show the relative sizes of the ions in your model. So the first thing you have to ask yourself is, which is larger, a Cu plus 1 ion or a Cu plus 2 ion? Cu plus 1 is going to be larger, and the Cu plus 2 is going to be smaller. Okay. And why is copper plus 2 smaller than copper plus 1? It's not the less shielding. It lost more electrons. So that means that the positive nuclear charge is going to have a greater attraction to the remaining electrons, so it pulls it in tighter, right? So the ion that would form a stronger Coulombic attraction to water, in this case, would be the larger one. Okay? It's going to be more difficult for water to separate a Cu plus 2 than it is for water to separate a Cu plus 1. Okay? There is a stronger attraction between smaller ions making it harder for water to separate them. Wow. I could have written that a lot straighter. Okay. So what that would look like is it's still going to happen. They're still going to separate. They're still going to take water, and they're still going to go ahead and like actually continue to separate each other. So like in this case, so this is going to be, okay. That's not what I wanted. I guess not. All right. So this water molecule here, because this is the negative side, is going to be attracted to the copper ion, and they're going to both be attracted. It's just that there's going to be a lot of Not a lot, but there's going to be a easier separation because the ion is larger. So in this case, it would look like this. Nope. And the closeness is not as important here as the fact that it's going to be more difficult to separate these two. More difficult to separate. Does that make sense?
So which one would form a stronger Coulombic attraction?
The Cu plus 1 would form a stronger Coulombic attraction. Any questions? We good today? All right. Well, that's pretty much where we're at. So that's as far as I was planning on going today. Perfect timing.